Hi everyone, I am Alessandro Umbrico, a researcher at the National Research Council of Italy. I present a joint work with other colleagues from CNR and from IRCCS-INRCA entitled Rehabilitation Support through Timeline-Based Planning. Nowadays, the definition of more sustainable healthcare services is crucial to face aging population and the growing cost of health assistance. One of the objectives of the research in surgery-assisted robotics is the development of novel care processes with the aim of moving from an in-hospital centralized assistance to in-house distributed assistance and thus design novel solutions that facilitate the interaction between the patients and the clinicians. Neurological disorders represent the leading source of disability in aging population, and Parkinson's disease in particular is one of the fastest growing. Researchers have shown that physical therapy at the early stage of Parkinson's disease is effective in counteracting the insurgence of motor symptoms. And in this context, novel interventions and physical therapies have been designed based on different types of dance, like, for example, Irish dance, showing promising results. And taking inspiration from these promising results, within the Italian research project C-Robotics, we are investigating the design of a novel dance-based rehabilitation supported by a social robot coach and supervised by a physiotherapist. In the realization of this scenario, automated planning is used to support the therapists in the construction of rehabilitation programs in shape of dancing sessions. Broadly speaking, the therapist provides a planner with input data about the session duration, so the song duration, and the desired clinical objective, and the planners gives as output a rehabilitation program consisting of a combination of dancing steps that are suitable for the desired objective and the considered user. However, to effectively synthesize such plans, there is a number of questions that should be answered in order to properly model all the needed knowledge into a planning specification. For example, some questions concern which are the definition of which are the set of stimuli and dancing steps in this case that a planner should consider to build rehabilitation programs, or also which are the set of constraints that should be satisfied in order to synthesize plans that are valid from both a technical perspective and a clinical perspective, so that satisfy the expectation of the therapists. And to this aim, we have implemented a therapist-in-the-loop modeling methodology that consists of three phases. A first phase, denoted with the blue box here in the picture, requires a really tight interaction between the planning expert and the therapist in order to define the set of stimuli and the set of features that support the desired clinical objective, so represent actually the basic data set on which the planning system is built. And a second phase, denoted with the green boxes in the picture, uses the gathered knowledge to define an actual planning specification, the planning behavior, and synthesize plans that are then used during the session. Clearly, a last step of a last phase assess the resulting sessions and the resulting rehabilitation programs, and eventually can start a new iteration of the overall process in order to refine the dataset of steps and features, and also refine the planning model in order to synthesize solutions and rehabilitation programs that are more effective with respect to the clinical needs. And so the very first step is the definition of a set of physical stimuli that are suitable for the considered scenario. We have perform these initial steps through tight interaction with therapists in order to identify which are the basic exercises or the basic steps that are complicated enough or difficult enough for being effective for the considered target of users. And we have defined a total number of 134 basic steps that are used as building blocks for the rehabilitation programs. So each step represents a particular type of motion of the user, during the execution of the session. And we can see here some example of the defined step, looking at the table on the right. And some steps, for instance, concern only motions on the lower or upper limbs of a user, while other steps may require the combination of simultaneous motion on both lower and upper bound of the user to define steps that could be more challenging from a coordination perspective. Then, given these steps, it is also necessary to define a number of features that would allow a planner to reason about these steps and properly concatenate them to synthesize plans. And so define a kind of metadata that is useful to allow the planner to reason about these steps and know how to concatenate them in a correct way, so generate plans that are technically valid, but also plans that are effective with respect to the clinical objective of the session. And so we have considered in particular two sets of features, a set of technical features that aim at characterizing the effect of each stimulus and each dancing step, in this case, on the environment and the body position of a user, and then a set of clinical features that aim at characterizing the effects of each dancing step on the health state of a user. Concerning the technical features, we can see that here that the set of parameters defined to characterize each dancing step with respect to their execution in the environment. And in particular, we can see here the features horizontal and vertical translation that have been used to denote the changed body position of a user after the execution of the associated step. To give a more detailed view of this and why this feature is necessary, here we can see a general and parametric representation of the environment that can be seen as a simple two-dimensional grid with a vertical and horizontal axis that delimit the available space of a user. The user is placed into the center of the layout and can perform some basic motions, like, for example, rotations, forward steps, backward steps, and so it is necessary to properly represent special constraints that would allow the planner to concatenate basic steps with maintaining the user within the grid, so within the desired space. And so in this case, spatial constraints and the overall layout of the scenario have been modeled using reservoir results into the planning formats that we have used. And broadly speaking, we can see the horizontal and vertical axis as two distinct resources, and motions as activities that consume or produce, depending on the direction of the motion, the amount of space available on the associated resources. So, for example, a rightward step of the user is represented as a production of the resource associated to the horizontal axis, and the activity in this case increase the amount of space available on the left side of the user, while at the same time reduces the amount of space available on the right side of the user. Conversely, a leftward step of the user on the same resource, so on the horizontal axis, is represented as a consumption of the resource, and in this case the activity decreases the amount of space available on the left side of the user, and at the same time increases the amount of space available on the right side of the user. So, in this way, modeling these spatial constraints in this way, the planner guarantees that all the combination of motions that have been planned always keep the user inside the box, so inside the desired layout of the scene. Then, concerning the clinical features, here we can see the set of parameters that we have defined to characterize how dancing steps interact with the health state of a user. In particular, these three features respectively estimate the amount of energy required for the execution of a step, and also the effort of a step with respect to the body coordination and the body balance. These features are directly correlated and connected to the desired clinical objective of the session, which means that While the technical features and the spatial constraints that we have described so far are always considered, so they are always taken into account by the planner to build the valid rehabilitation programs, the clinical objectives, subset of clinical objectives are considered according to the specific objective design for a given session. So currently we are considering two clinical objectives. One objective concerns the stimulation of maintenance of the equilibrium of a user, and in this case, as we will see next, the clinical features evaluated are the coordination and body balance, while another objective concerns the stimulation of the metabolic response of a user. And in this case, clinical features evaluated are the coordination and the energy of the steps used within the rehabilitation program. All this information, constraints, and the logic used to build the rehabilitation programs have been implemented and developed within a timeline-based planning framework. The timeline-based approach has been introduced in the early 90s and has been successfully applied in several real-world scenarios, mainly thanks to its capability of integrating planning and scheduling. In previous work, we have proposed a formalization of the main concept of the timeline-based approach by formally characterizing state variables, tokens, and also integrating controllability issues. And we have developed a general purpose framework called Platinum that complies with the proposed formalization. Our research team, as you may know, has worked with timelines since many years and mainly in space application scenarios. While more recently, we have applied this technology to manufacturing, and we are currently using Platinum and the timeline-based approach to coordinate collaborative sets in human-robot industrial collaboration. And in this case, to support the rehabilitation scenario described, we have extended Platinum with Pareto-based heuristic search in order to evaluate and integrate reasoning on heterogeneous features of a plan. And also to integrate different heterogeneous parameters that can be combined different ways according to the specific needs of the application scenario. So the search is structured using an A-star based evaluation function in a similar way to some other works in the literature, like those cited here in the slide. And each node of the search space is evaluated with respect to a number of metrics and features. So for each feature considered within a particular clinical objective, for example, we evaluate the evaluation function combines a cost function that estimates the feature with respect to the consolidated part of the plan with a heuristic function that estimates the minimum expected cost of a plan with respect to by taking into account the possible refinements of the partial plan. An evaluation function on different features using the Pareto-based approach are integrated using taking into account the concept of Pareto dominance. This allows planners to move the search toward the Pareto set, characterizing plans that achieve a good trade-off among the considered metrics, and also to integrate heterogeneous features in a general way. So this organization of the search supports the integration of different features and also different search behaviors that can be achieved by implementing different search strategy that focus or consider different subsets of the features of a plan. In this case, we developed dedicated search strategy for each clinical objective considered within the scenario. The search strategy for the equilibrium maintenance evaluates, for example, plans by taking into account the features, balance, and coordination. The objective in this case, indeed, of the search is indeed to find a solution find a plan that stimulates the ability of a user of maintaining the body equilibrium, and thus from an optimization point of view, this can be seen as the problem of maximizing the cumulative effort on body balance and coordination required by a plan, so required by the steps that have been selected for building the rehabilitation program. Similarly, the search strategy for the metabolic response evaluates the plans by taking into account the features, coordination, and energy. In this case, the objective of the search is to find a solution that stimulates the physical resistance of a user, and thus, from an optimization point of view, a rehabilitation program that maximizes the cumulative energy required for its execution, and so while at the same time maintaining low the coordination effort, so to keep the single exercise as much simple as possible. And here we can see an example of a synthesized timeline-based plan that represented as a Gantt chart with timelines projected on the earliest start time. Some abstract timelines describe the high-level task of the rehabilitation program. This task is then decomposed with an intermediate timelines that describe the structure of the rehabilitation program in terms of a sequence of blocks of patterns of steps, so groups of steps, and these patterns, also these blocks, are further decomposed into a final timelines, which is the primitive, so to say, primitive timelines that contains the actual physical steps, and so the dancing steps that are performed by the user during the execution of the rehabilitation session, and so these timelines represent the steps selected by the planner to support the associated clinical objective. To evaluate the technical feasibility of the developed framework, we have performed a number of experiments by varying some domain parameters in order to define problem instances of growing difficulty. All the runs have been performed on the same dataset of steps, clearly, and on the same set of features that have been validated and defined through the interaction with the therapist. And in particular, three configurations of planning instances have been tested. The configuration OB1 is designed to support stimulation of the equilibrium. The configuration OB2 is designed to support the stimulation of the metabolic response. And the last configuration, DFS, is designed to evaluate the framework without the contribution of the multi-objective heuristic search. Results shown in the paper point out some initial but promising achievements, so promising results, as they show the capability of the general framework to adapt its choices and adapt the shape or the feature of the generated plans according to the desired clinical objectives. However, some work was necessary to improve the scalability of the planner to solve more problems, as well as also refine the search and the dataset to generate more effective solution. Looking at the results, this was especially necessary for the stimulation of the metabolic response, where the planner showed the worst performance in terms of number of solved problems, quality and qualities of the obtained solution that were not so effective as expected for that specific clinical objective. And after the acceptance to the workshop, we have continued working on this, and here we can see some new results, a summary of some new results that we have obtained. And as we can see, the performance has been significantly improved, leading to a planner that was able to solve a relevant number of additional planning instances within an average time of 75 seconds. And furthermore, we were able to solve also problem instances that with some duration of 180 seconds that were not considered in the previous experiments, because the planner wasn't able to actually to find a solution in reasonable time. And finally, the results show also improved performance with respect to the qualities of the choices made by the planner, and thus the features of the generated plans and the generated rehabilitation programs. Indeed, as we can see in this case, the generated plans are more effective with respect to both the objective of the clinical objective of the scenario. So to conclude, we have shown in this work how the use of planning to support the synthesis of rehabilitation program. On the one hand, we have described a therapist in the loop modeling approach that was needed to define the complex knowledge and information needed to build valid, correct, and effective rehabilitation programs, and so effective plans. And on the other, we have shown how an existing timeline-based planning framework has been extended with multi-objective features in order to support these scenarios and integrate the different features that were relevant for the considered cases. Next works will consider, of course, an extended experimentation of the developed technology with real users and the integration of learning mechanism in order to enhance the search through the and also the integration of learning mechanisms to enhance the search through the synthesis of specialized heuristics in order to be more effective in solving specialized problems. This concludes my presentation. Thanks for your attention.